In this session, few problems on commutator relationships is presented here. The commutator x cube px is equal to, we need to find the value of the commutator x cube px. For this to be solved, we need to be knowing this relation. The commutator of x power n with px is equal to n into x power n minus 1 I h bar. So use this formula and you just write this according to this formula. Here we have x cube px. Now this would be equal to 3x power n minus 1. And is equal to 3, then it will become x square I h bar, and it will be 3x square I. Instead of h bar, you can write h bar in terms of h as h by 2 pi. Then coming to this step, you just divide and multiply by I both in numerator and denominator. Then simplify, you will get the value 3h x square by 2 pi I minus 3h x square by 2 pi I. So this would be the answer. The only thing you need to know is, you know this formula, x power n, the commutator of x power n with px is equal to n into x power n minus 1 I h bar. Then it would be very easy to solve this problem. So the other problem here is the value of commutator x xpx is, now here we have a commutator within a commutator. We have a commutator within a commutator. So we need to find the value of that. The value of the commutator x xpx is equal to, then you must be knowing the value of the commutator xpx is equal to I h bar. You can also come to this value by using the earlier expression where x power n px is equal to n into x power n minus 1. In this case, the value of n is 1. If you substitute that, you will get this, or directly you can remember this as the commutator value of xpx. The commutator xpx is equal to I h bar. Then at this position, the commutator value is written here. Then we end up with the total commutator, the xpx. And one must be knowing this, the commutator value will be 0 when operator commutes, when this commutator relationship is written with a constant. A operator and a constant gives the value 0. So here is one more problem we have. If x and px are the x components of the position and momentum operators of a particle respectively, then the commutator x square p square is equal to, then we need to write this x square p square is equal to x square, then p square is written as p into p. This, now we should expand this p square p as this formula. This is the formula used to expand this commutator. Now, if A, B, C are commutator are operators, when you take A, B, C and the commutator operators, then the value of the commutator of the type A, B, C is written as, now B times the commutator AC plus commutator AB times C. Now, how do we write this is, if you have a commutator A and the product of two operators, the commutator of the operator A with the product of two operators is written like this. Now this B will go to left, then we are left with A and C, that is written here. Then this C will come to right side. Then we are now here left with the commutator AB times C. That's why we should remember this formula. Then now we'll expand this x square PP as this, the commutator of A and product of two operators BC. Now we will send this P onto left side, it will become P. Then what is left here is x square P, that is written here, plus now this P would come onto right side, then whatever is left should be written within the commutator times P. Then the value of this P commutator value of x square P is written according to this formula as 2x I h bar, plus same is written according to this formula, then 2x I h bar P. Now you take the common out 2i h bar. Now we are left with px plus xp. Now we cannot add these two px plus xp. So we know that when a and b are operators, ab is not equal to ba. Then the value of this commutator x square p square is now equal to 2i h bar px plus xp. px plus xp. The option 4 will be the answer. Now in this form, the problem here is let L and P be the angular and linear momentum operators respectively. L is the angular momentum operator, P is the linear momentum operator. Now we need to find the commutator Lx Py. The commutator value of the commutator Lx Py gives. For this to solve, we must first be knowing how to write the linear momentum operator in terms of the angular momentum operator in terms of its linear components. This angular momentum along x is equal to y pz minus z px. Here y and z are the linear coordinates and pz is the linear momentum along z axis, and here px is the linear momentum along x axis. Now what is done here is the angular momentum is written in terms of the linear components. Then you should also be knowing these two commutator relationships. If A, B, C are operators, then the product of two operators with the other operator C, the commutator of the product of two operators with another operator C is now written as A times the commutator BC plus commutator AC times B. This is written as I told earlier how this is the product of two operators. Now from this we should take A onto left side, then we are left with the commutator B with C, then B is coming onto right side, then we are left with the commutator AC times B. That's how it should be written. And other formula you should also remember with respect to this commutator relationships is our commutator algebra is the commutator of A minus B with C is written as commutator AC minus commutator BC. Now we'll start with this commutator LX PY. The commutator LX PY is equal to, now LX is written in terms of linear components ypz minus zpx with py. Then this is now expanded using this formula. Now this could be now written as ypz commutator of ypz with py minus commutator of zpx with py. Now in this case, this ypz, here y and pz also are the operators, the product of two operators, the commutator of product of two operators with one more operator py is now expanded according to this formula. Then y once comes onto the left side, then pz would come onto right side. Remaining will be written here. That's when y is taken left side. Now we are left here with pz py, commutator pz py. When pz goes onto right, then this will be written y pz y commutator y py pz minus. Similarly, this the commutator of product of two operators with one more operator is again expanded according to this formula and is now written here. And in this case, all the commutators here pz py, px py, z and commutator z with py will become 0 except the one which is highlighted, because the position and momentum in the same direction don't commute. The position and momentum in the same direction don't commute, so this would not become equal to 0. So the value of y py is I h bar times pz. So the answer for this question is I h bar pz. Now to solve this problem, we need to be knowing these three formulas and also the idea about the commutator values. What kind of a commutators would commute and what kind of a commutators would not commute. The commutator of a position and the momentum in the same direction will not commute. If they will not commute, whose value will not be equal to 0. And these two commute, these two also will commute, these two also will commute. The meaning of commute is the value of the commutator is 0, or in other words, you can find the value of the these two operators z and py in this case simultaneously and accurately. If we are not able to find the value of the two operators which are constituting this operator commutator, then it will not commute. Then that's how this will commute. This will also commute. If it also commutes, then the value of this will be 0, but the value of this is not equal to 0. The value of this is I h bar p side. The other form, the other question here is this. Here we are given two operators, a plus and a minus. A plus operator is defined like this. A plus is equal to 1 by root 2 x plus ipx, and a minus operator is equal to 1 by root 2 x minus ipx, where x and px are the position and linear momentum operators. The commutator a plus a minus is equal to. So this could also be your rising and lowering operator. You could take it as. Then next we'll first start with this commutator, and then we should write the commutator a plus a minus can be expanded like this: a plus times a minus minus a times a minus times a plus. Any a general commutator, if you take a and b, the commutator of the operator a with operator b can be written as ab minus ba. That's how here is written. Then we should write the value of the rising operator a plus and the value of the lowering operator here minus. Again same, write these two values here. Then we'll just simplify this: 1 by root 2 into 1 by root 2, 1 by 2, and multiply this x plus ipx and x minus ipx. You will get this 4 terms. Similarly, do the same thing here. Then also you will get 4 terms here. And in both the cases, we have 1 by 2 common. If you take common out, then this is what you will get. In this step, the terms which are highlighted will get cancelled. Then we are finally left with 1 by 2 to I px x minus 2I x px. Now we cannot cancel these two because the operators, the operator AB is not equal to BA. That's how we should not cancel this. Then again, what is common here is again 2I is common. When 2I comes out, we are now left with px x minus xp. Then now this is the value. If you take 2I outside, this 2, 1 by 2 and 2 gets cancelled. We are left with only I outside. Now within we have pxx minus xpx. Now if you just express this form, AB minus BA, when A and B are two operators, then AB minus BA can be written as commutator AB. Now we are just going from right to left here. So right to left, when if Px is an operator, X is an operator, and AB minus BA is written as commutator AB. In this case, A is Px, B is X. Now this could be just written like this in this form. Then the value of that will be I into commutator Px X. Earlier there was no square bracket. Now we introduce the square bracket just to tell that it can be commutator form. The value of the commutator Pxx is minus I h bar. Earlier we used the values of the commutator xpx as I h bar. Now it is reversed here. Pxx, the commutator Pxx is written as minus I h bar, because we know the general relationship. The commutator AB is equal to minus commutator BA. We use that, then we will get this value to be minus I h bar. Then we will just simplify. You will get the answer as h bar. So that is your answer h bar here. And one more problem here, which was asked in December 2017 exam. If A and B, the commutator AB is equal to 0 and the commutator AC is equal to 0, And now, in other words, how do we read is the commutator AB and B commute. The operators A and C also will commute. Then which of the following necessarily holds? Here A, B and C are operators. Now we will take the option 2. This is the option 2 is taken here. Then now this is the commutator of an operator with the product of two operators. Here A, B is here operators. Now we are constructing the commutator with the operator A and the product of two operators. Then according to earlier equations we have seen, when you expand this kind of a commutator, you will get B would come onto the left side. You are now left with the commutator AC. Then C will come onto the right side. Then you are left with the commutator AB and C would be coming out. Now from the given data, the commutator AB is 0 and commutator AC is equal to 0. Commutator AB, the value of this commutator is 0 here and the value of this commutator AC is 0 here. Then the commutator of A with the product of two operators BC is equal to 0 because the value of this is 0, then this is 0. When reduce the values of 0, then you will get 0. So the answer for this question is second. When you do the same kind of expansions with this, then you will not get the answer to be 0. And here is one more problem. The commutator of X is the position operator, is the Hamiltonian H, where H is the energy operator. We need to find the value of this commutator X, H is. For that, we must be knowing the corresponding operator for the energy operator H. H can be written as H is equal to minus H bar square by 2m d square by dx. This is the corresponding operator form of this energy. Then X, for X is the same X as the corresponding operator form. Then we need to now find the value of the commutator X with H. So we cannot find the value of the commutators of any two operators in isolation. So we need to have a wave function psi of x. Then must expand this commutator xh as xh psi x minus hx ab minus ba. If you take this as AB, then AB psi x. Now, if we just go to another step, AB commutator AB psi x is equal to AB minus BA psi x. Then psi x is written individually. That's all. Now, this is the x. Now, what is done from here to here is x is written as such as x, and h, the operator form of h is written instead of h. The operator form of it is written. Then psi x is the wave function minus here instead of h its operator form is written and x psi x is written as such. Now we need to we need to do the double differentiation of psi x here. Then we need to do the double differentiation of x psi x, but this we should follow here the differentiation of product of two functions, differentiation of a b with respect to ax, where a and b are functions of x. If you do that, then you just be simply doing the differentiation of the product of two operators here. Here it is shown that the first function to differentiation of the second function plus second function into differentiation of the first function will become x will be a differentiation of x with respect will be 1. Then earlier we were having here d square by dx square as we did one time differentiation. Now it has become d by dx. And second, if you do the differentiation of this term plus this term, then keep doing it, follow the same thing, and finally you will end up coming to here, follow all the steps, do differentiation twice and simplify it. Then you will come here. At this stage you need to introduce the corresponding momentum operator. The px is the momentum operator. The momentum operator px can be written as minus I h bar d by dx, minus I h bar d by dx can be written as px. Now here we are left with one more I and H, as we have H bar square here, H bar square here. One H bar is enough for writing the Px, and now we take this as the H bar. It's not as H. That's all is the problems about this commutator relationships.